I'm Todd Austin from University of Michigan. This presentation, called On the Rules of Computer Engineering and How to Break Them, was a short presentation I gave at this year's Micro Conference in Austin, Texas in November of 2024 upon receiving the IEEE Computer Society Bob Rao Award for 2024. This talk is about how do you find research that has good potential for impact again and again and again over a career. And the approach that I take is something that I call a rule breaking approach to research. So let's take a look at this short presentation. So I want to start by just going back to where it all started. This is the first piece of research I did at University of Michigan. It came out of my experience at Intel. Before I came to Michigan, I was a computer architect at Intel. And it came out of my experience at Intel where I came to the realization that almost everybody at Intel does hardware verification. Of course, they have to because it's incredibly important that the hardware be functionally correct. And so I wanted to figure out a way to build a piece of hardware that could decouple correctness from performance. And so I had this goal, let's build a piece of hardware that could tolerate its own design errors, because then you'd only have to be able to get rid of the design errors that you could find, and all the rest of them would be corrected by the design. And this led to Diva, which stood for Dynamic Implementation Verification Architecture. The way Diva worked is it was really two different processors. On the one hand, you had the core as we would typically build it, which was a big complex core and difficult to ensure that it was completely correct because of the extreme complexity and the inability of formal verification to really reach inside there and make strong assertions about the correctness of this design. But it was fast. Then on the other hand, you had this second core, which sat right before the commit stage of the pipeline, called the checker core. And the checker core was very simple and formally verified. The checker core was just a simple little unpipelined 5-stage pipeline. And normally it was very efficient at checking the instructions to see if they were correct. And then in the event that it found one of the instructions got a different result, if the performance core disagreed from the correctness core, you would just retire the result of the correctness core because that had been formally verified and the performance core had not been formally verified. Well, people always ask the question with Diva is, if the checker is so good, why do you need the performance core? And the reason is because by itself, the checker is very, very slow. It's about 15 times slower than the performance core. But with the performance core, using the performance core as a branch predictor and as a value predictor to create extra parallelism, the checker is extremely efficient and has no hazards at all. So a very simple pipeline following the performance core can execute instructions very efficiently and be formally verified. And so what you end up with is this design that can tolerate design errors in the performance core. After I had completed this design, about a year later, I went back to Intel and I presented this work, and I came to Intel saying, "Oh, look, I've solved all your verification problems." And I remember giving the talk about Diva, and then after the talk, multiple people coming up to me afterwards and saying, "We can't do this. No, we can't do this. You cannot release a core that has bugs in it." And then I would explain to them, I go, well, they're not really bugs anymore. If they're in the performance core, then they're just causing resets of the pipeline when the correctness checker corrects the instructions. So really, it's just a performance issue at that point. But I could tell that this idea of releasing something that potentially had bugs in it was an anathema to the designers that were working there. And this was really because Diva had broken a fundamental rule of microprocessor design, which is that you cannot release your microprocessor until you've found and corrected all your bugs. Of course, anyone that works in verification knows that's more of a guideline than a rule, because you're not going to be able to find all of your bugs. It's just not possible. There's too much complexity, too much state there. And what I discovered is that this Diva checker mechanism is really powerful. It's a form of verified computation, and verified computation can handle design errors, it can handle electrical faults, you can run at low voltages and correct the faults in the main core, it can handle defects, it can handle soft errors. It even handled issues, correctness issues that materialized decades after the Diva implementation was proposed, including hardware Trojans and SDCs, something that the industry is now battling with today. So really interesting design, and got me really started on this idea of rule-breaking approach to research. So what is a rule-breaking approach to research? It's very simple. One, find a rule that nobody breaks in your field. It's a rule that's typically taught very early on. And that rule creates dogma in the field. And I like to use the word dogma because it's almost like religion. To break this rule is to basically become heretical in your field, right? So for example, in verification, you don't release anything that you think could possibly have a bug in it. In security, you don't try to build a system that cannot be hacked. And these are rules that cannot be punched through because they're so ingrained into the field. The second thing you need to do is you need to find a way to break that rule. Now that can be very challenging, and often initially the way you break that rule is completely unrealistic. But an unrealistic way to break that rule will get you to the other side of it, and that's where step 3 comes in, where see what happens. How does the landscape of optimization and design and efficiency improve once you break that rule? And that's a really interesting place to be. Even if your way to get around that rule is inefficient, over time you can improve those efficiencies. So, don't set the bar too high initially. The thing that I learned that was particularly exciting about this approach to research is you really engage your community when you start breaking these basic rules of design. And what you'll notice is that, roughly half the people that are exposed to your research will really love it and think it's an amazing idea, crazy, but amazing. And then the other half of the people will think, this is not right. This should not be done. This violates the rules that we should never violate. And I always say, embrace that pushback, because that pushback will inform you that you are going into new territory, and it'll help you sharpen your framing of how you present the work to really make a strong case for it, that we need to break those rules. Often people of great stature will take a piece of my work and say how it's bad for the community. And for young PhD students, that could be really upsetting. But for me, it's incredibly exciting. I love it when people do not like my research, especially people that are well established in the field, because then there's an opportunity that I'm actually breaking through this dogma in a real materialistic way. All right, so let's take a look at some of the rule-breaking work that I've worked on in my career as examples of how breaking a rule can have some great benefits. So we saw the very first piece of work I worked on, which was Diva, this idea that we're going to break the rule of your CPU is not finished until all your bugs have been found. Well, in this case, we're going to release the CPU with potential bugs in the performance core that be corrected by the correctness core. One of the frustrations I had with Diva is industry didn't want to build Diva. So I thought hey, here's a way to get rid of, basically 6/7 of your design team costs and put all those people on design, because now you don't have to verify as aggressively, but that didn't happen. So a few years later, that led to a project called Razor, and Razor was initially called Baby Step Diva because it was like the minimalistic form of Diva that somebody might adopt. And the goal of Razor was simply to build a CPU where not every stage of the CPU, not all logic in every stage completes in a single cycle. And if a particular stage logic does not complete in a single cycle, there was this Razor latch which would detect a late arriving signal and then would initiate a pipeline recovery to fix the state of the machine. Now, the reason we wanted to do that was because we wanted to essentially shave voltage margin until there was this moment where you were getting these constant errors. And this was very rule breaking because it created metastability problems. It violated the basic rule of timing closure in circuits. But on the other side of that rule, what we discovered is about 50% of the energy in the circuits is just for reliability. And there's been, this particular line of work is very rich, and there's examples of compiler work and dynamic scheduling optimizations that can even further increase the amount of slack that exists in these designs to go to even lower energy states. This one is getting closer to being implemented by industry 18 years later, as we get to the point now where Moore's law has ended, and we're looking and searching for one-time optimizations that can provide great power efficiency and computation. People are starting to look at Razor, so hopefully that'll find its way into industry soon. Continuing on this line of ultra low power designs, I worked with a student, Leila Nazandali, who's now a faculty member at Virginia Tech, and we designed together with David Blau, a professor here at University of Michigan, what we call the Subliminal processor, which was really taking a processor to the lowest energy state possible. When you lower voltage and save energy, you ultimately hit this point called the threshold voltage. This is the voltage at which a transistor turns on. And you don't go below the threshold voltage because then your transistors don't turn on and you're no longer computing. So working with Leila and David, we broke that rule and essentially lowered the voltage below the threshold voltage and then built a CPU that computed by modulating leakage of all turned off transistors. So Subliminal was a CPU that had never turned on a transistor ever, and it computed by just modulating leakages at slightly higher low voltages and slightly lower low voltages. And what we discovered on the other side of that was, oh my gosh, you can get to ultra low energy states. At the time when we did the first tape out of that chip, it was the most energy efficient design ever created. And then this led into work involving not just reliability for low power, but also reliability for reliability. There was a concern around the time of this work that reliability would ultimately end Moore's law. Like as we got to smaller and smaller devices, defects and soft errors would ultimately limit how small we could make devices. So there was a push in the community to find really low cost reliability mechanisms. And at the time, if you wanted to do defect tolerance, you needed like triple modular redundancy, 200% overheads, really, really ridiculous. So, working with some colleagues here at Michigan and students here at Michigan, we came up with this idea of essentially breaking the rule that manufacturing tests run at fabrication time once, and we packaged up all the manufacturing tests and we put it on the CPU. And then in idle cycles, whenever a unit was idle, we would inject these tests into the design and essentially discover when something had become a defect. And when something had become a defect, we also had a very low cost checkpointing mechanism, which essentially checkpointed to the caches and snapshot the register file, where we could then roll back before that defect and then work around, disable that component and work around that defect. And it took, this 200% defect tolerance for triple modular redundancy down to under 5% overhead. This is an idea that's still really being pursued actively in the community as well. Sometimes when you want to find a rule to break, you just pick one and go for it. You're not really led to it by other work. And this was really the case for a project with Martha Kim, she was a grad student at the time at the University of Washington. She's now faculty at Columbia. And Mark Oskin, who's a faculty member at University of Washington. we were sitting around one afternoon postulating what kind of rule could we break. And the rule we wanted to decide to break was you cannot fabricate silicon in your home, right? You cannot bring silicon fabrication into your house because we really want to design custom logic in our house. Now, of course, you can do this with a FPGA, but the FPGA is not a very satisfying approach due to the high power constraints and the large area costs. We really wanted to find a way to fabricate silicon that would be comparable to an ASIC design, maybe 5 or 10% slower. And this led to what we proposed in 2006, brick and mortar silicon. This idea that you would take the silicon components that you use to build systems on a chip, you would break those apart into little flakes of silicon called bricks, and you would place them onto a silicon backplane called the mortar, and the backplane was typically going to be just passive logic, a bunch of wires, and or it could be active with routers, and you would just basically put these chips onto there, and you build your system. And so your system composition would be from this ecosystem of these bricks, and then you'd get the yield advantages, the low design costs, the low NREs, et cetera, et cetera, et cetera. This was in 2006. This is chiplet-based manufacturing. This paper is the seminal paper in the domain of building ecosystems of chiplets. So really, really proud of this work. In 2011, I took a sabbatical, and during that sabbatical, I went to Ethiopia and taught. Why did I do that? That's a whole nother story, but I do a lot of work in CS development in Africa, and so that really started in Ethiopia. When you teach a class at Addis Ababa Institute of Technology, where I was, it's not like the US where you sort of have this palette of classes and then students pick which class they want. In that particular program, it's a set menu. So the semester I arrived, they just looked at me and said, hey, guess what? You're teaching this class, security. And I didn't know much about security. But I said, yeah, I'll teach the class. What a great opportunity that was, because in teaching that class, I really fell in love with computer security. I think if I would have been exposed to that at the beginning of my career, I probably would have spent my whole career doing security. Today, I do a lot of security work. I'll just say briefly, the reason why I love security so much is unlike all the other areas of computer engineering, where you're up against physics and complexity, in the area of computer security, you're up against the evil genius. And it's just an endless, endless challenge to overcome the evil genius. Okay, so that led to, initially me working on a number of attacks, right? And the majority of the security community is doing attacks. And that led to an attack called the A2 malicious Trojan, which was a 3-transistor backdoor for Linux installed inside an open source CPU, which we manufactured and then demonstrated that attack. And it was, the rule it broke was that, hardware Trojans at the time were thought to be you could see them and detect them with power analysis. So we designed a hardware Trojan that was 3 transistors, too small to see optically very, very well. I mean, you certainly couldn't search for it. And it was passively powered. And it used analog logic, so it was very low power. And it worked really well. This one definitely was cutting edge research, because we got a lot of pushback on this work, but it really helped reframe the concern about Trojans. In particular, this was one of the very first pieces of work which suggested that a Trojan could be inserted at manufacturing time. After spending a number of years working on attacks, I wanted to then go work on defenses. And like most computer architects wanting to work in hardware security, my initial designs were incredibly complex. And Morpheus was an initial design that I worked on. Morpheus was a pretty wacky thing. It was inspired by the human T cell. Why the human T cell? Well, the human T cell is your security system, and it adapts to new attacks. You know, when COVID comes flying into the world, everybody's immune system adapts to it. How does it do that? Well, by studying those mechanisms, we can come up with better computer hardware security mechanisms. So Morpheus was based on it. It was very complex, had lots of instructions and tagging and et cetera, et cetera. And we were in a program where we were implementing Morpheus in Chisel, which is a novel a hardware description language that's used often in the RISC-V world. It was based on it. We were enhancing a RISC-V processor design. And during that project, I learned a bunch of stuff. But one of the things I learned is I'm not smart enough to use Chisel. And I'm not smart enough to teach my students how to use Chisel. And so the project just was slipping behind schedule to the point where we were going to lose funding for the project. So midway through the project, I said, okay, we designed the project so that the encrypted pointers, which was sort of Morpheus' special capability, were always decrypted when they went into the L2 cache, the L1 cache, the registers, right? This was a rule that was never violated. It's not even written down, but it was never violated ever in computer architecture. And I said, we're not going to get this tagging to work. Just keep the pointers encrypted everywhere. They're encrypted in the registers, they're encrypted in the caches, everywhere. We'll deal with the performance issues later. And what an amazing discovery that was. We not only got the design working on time with this very, very simple approach, but we got into the third phase of the funding where there was actual red teaming occurred, and we were the only design that wasn't penetrated. Why? Because we encrypted pointers everywhere. It didn't matter how much access you had to the system. If you didn't have the keys, you couldn't figure out what these pointers meant. So super powerful technique in breaking that rule just out of desperation. Towards the end of that project, one of my program managers who was funding the project, you know, we had this great name, Morpheus, right? And our program manager, he kept calling it HE pointers. And I said to my program manager, what is this thing HE that you talk about? And he says, oh, it's homomorphic encryption. Your pointers are always encrypted anywhere. It's like homomorphic encryption. So I went off and started reading about homomorphic encryption. Amazing. The reason why people are so excited about homomorphic encryption is because it breaks a fundamental rule of programs, which is that a programmer can see the data that they are computing upon. Never before homomorphic encryption had this rule ever been violated. Programs own the data. They see the data. They decide what's being done with the data. But in a homomorphic encryption system, you're doing computation directly on encrypted data without access to a decryption key. So you're doing computation in a program on data you cannot see. That is so powerful for security because if someone hacks into the program, they only get to steal ciphertext. But it's even more powerful than a security technology. It's actually a privacy technology. Using that basic mechanism, you can decide who sees the data. Maybe the data was encrypted by someone else. They've sent you their genome, but you on the system cannot see that underlying data. So what an amazing technology that was. So I started to study it. Now I'm a hardware guy. All my solutions come from hardware. The problem with homomorphic encryption is it's basically a hot mess today. It's hard to program. It's super slow. It's limited capabilities. And so I thought, like, just push all the HE stuff aside. Take the rule they break, which is that programmers can see and modify all their data, and re-implement it in hardware. And this has led to sequestered encryption, the work that I'm currently working on, which breaks that rule. Let's durably hide data from hackers. That's good security. IT staff, that's good security. And programmers, that's good privacy. Right? By not having to trust anything about a system, including its operators, including the programmers, you really create a basis for great privacy technologies. So how does sequestered encryption do this in hardware? Like homomorphic encryption does this in advanced cryptography. Well, all it does is add a special functional unit. The claim of sequestered encryption is that the ills of security and privacy in the world can be completely solved with one functional unit. That functional unit takes encrypted data and processes that encrypted data, which always begs the question, how does the functional unit get access to the data? Well, that problem was solved in 1976 when they invented public key cryptography. So the functional unit in your pipeline has a public key that it publishes to the world, and internal to it in its hardware has a private key, and it can use PKI technology, key switching technologies, invented in 1976, to put a key inside of it. Now you have this very small, trusted hardware component that can compute directly on encrypted data. Encrypted data goes in, it computes on it, encrypted data comes out. And it's not just adds and multiplies like fully homomorphic encryption, it's a full risk instruction set with conditional moves, so you can do conditional processing and all kinds of stuff. Combine that with formal verification, and you can end up with some very powerful technologies. But you can even extend it more. We've extended it to do integrity checking of the computation, integrity checking of the data that it's computing upon. So it essentially, where FHE technologies only deal with confidentiality, we can deal with the entire CIA of security, confidentiality, integrity, and availability. And what great discoveries. Where FHE would typically slow your machine down by hundreds of thousands to millions of times, depending on how capable the programming framework is, this is a 15% slowdown. And that functional unit, 190,000 gates. We've deployed this technology in Azure and AWS in my startup at Gita Labs, and it's been red teamed. The red team was not able to violate our security constraints. And then we've also formally proven that this thing doesn't leak information either directly or indirectly through side channels. So really powerful stuff. So powerful that in the marketplace, this technology competes with privacy technologies like FHE, multi-party computation, zero-knowledge proofs, and private set intersection. So really exciting work. Again, breaking this rule that we're not going to let programmers see all their data. And then I'm going to end the talk just with, other rules that I'm thinking about breaking. I'm not going to go through all these right now, but these are things that I think about a lot in my work. And I tend to find I grab onto a rule and then I think about it for, probably 10 years. These are things I've been thinking about for a long time. And then also I wanted to present you, I have a research partner, which I've started spending a lot of time with. And I went and suggested to my research partner, give me some suggestions that I can use as well. Of course, my new research partner is ChatGPT. I gave it the earlier part of this talk and said, give me 30 examples. And I called out the top few here. Some pretty good ones. This is what I really like. Data compression is only for storage. That's like a riff on FHE, but instead of encryption, it's compression. Oh, I love that idea. A lot of compression happening in the data center. And arithmetic must be binary. I mean, if you look at how Moore's law progresses today, it's really through, better arithmetic representations. So that's certainly one rule you want to think about potentially breaking. Anyway, and then I have a few acknowledgments for all the people I've worked with. Of course, my students, I have to acknowledge, as a research professor, I tell my students, I don't do research, I watch people do research. So all this work was really done by other people that I had a chance to mentor. And it's a great privilege to be able to work with my students. And then, I love to collaborate. I really see 1 + 1 = 3 in the collaboration. And this is a picture of the Ada Center, which was a big computer engineering center at University of Michigan from 2017 to 2022. That was a lot of fun to collaborate with so many people in that work. And then I'm also really very much grateful to my sponsors who over many decades have sponsored this work, and my students as well. So I really appreciate them as well. Thank you so much for watching my talk. And if you have any questions, if you want to tell me about the rules you're breaking, often people after this presentation will tell me about that. Hey, just shoot a comment on this video or message me on LinkedIn. And best of luck to you on your research journey as well. Take care.